Hello, everyone. Welcome to the next session of our Manufacturing Industries track here at GTC 2015 Silicon Valley. So glad you could join us. My name's Andrew Rink from NVIDIA, and I'm very pleased to welcome our next speakers here from SpaceX. We have Adam Lichtl and Stephen Jones. Stephen is the lead engineer of the Simulation and Analytics Group, where he works on large-scale simulation of combustion processes in rocket engines. He has expertise in computational fluid mechanics and plasma physics. Funny, so do I. And is a former NVIDIAN who has spoken at almost every GTC. And Adam is the director of research and is responsible for identifying and developing technologies to advance the company's mission, which is transporting and sustaining a human colony on Mars. His background includes work on particle accelerator design, simulation of combustion devices for chemical rocket propulsion, and high-density power generation systems. I understand Adam also has a grasp of basic conversational Martian language. So, launching the microphone over to SpaceX to share the story of their full-scale simulation of SpaceX's Mars rocket engine.
Thank you. Thank you very much. And thanks to NVIDIA for inviting us to give this talk. Thanks to all of you for coming to see us. And I want to thank SpaceX for encouraging this research and allowing us to share a little bit of our ongoing results. SpaceX is an American company that creates and launches its own rocket fleet. We have operations in California, Texas, and Florida, and were founded in 2012. To date, we have 18 successful missions to date, and we fly the Falcon 9 rocket. We design our own engines. We build them in-house. We test them in Texas. And finally, we integrate the vehicle and launch.
10, 9, 8, 7, 6, 5, 4, 3, 2, 0. Lookup. Falcon 9. Falcon 9 has cleared the tower.
We launch satellites for private companies. We launch our Dragon capsule to resupply the International Space Station. And we also launch satellites for government organizations. In the future, we hope to take people back to space on American vehicles. In addition, the real goal of the company from day one has been to get humankind to Mars. For any sort of meaningful exploration of space, this is the next natural stepping stone. Mars has an atmosphere. It has similar overlapping temperatures to Earth. It's cold, but it's not ridiculously cold. The atmosphere is thin, but it's present, unlike on the moon. And the soil contains water underneath. To get to Mars, there are many challenges. And a lot of very brilliant people in NASA and other organizations have looked at this problem. One of the major problems is that of radiation exposure. To get to Mars, you have to align your launch with the correct window to get to Mars on an orbit, given the amount of energy that your rocket can produce. So anyone who's played Kerbal Space Program has seen this. But the key thing here is delta V. It's the change from one orbit, say one around the Earth, escaping that, doing an escape burn, giving yourself a delta V to put yourself in a different trajectory that will intersect with that of Mars. We need vehicles that can provide as much delta V as possible in order to shorten that trip to Mars. In addition, a second major obstacle of actually staying on Mars, not just taking a rover or a machine or a one-way suicide trip, but a real expedition to Mars, is infrastructure. When the pioneers went across the United States, when they got to where they were going, they had to build their own cabins, they had to hunt their own food, but they had air. So it's a little bit more tricky on Mars. In order to really sustain any sort of colony on Mars, you need a tremendous amount of infrastructure. You're going to need to have the ability to generate power for heat and for melting water. And importantly, you need to be able to come back and actually have a way to return. And I'll come to that in a moment. But on this slide, I just want to point out that the amount of mass we actually should send to Mars for even an initial mission with people on it is tremendous. It's comparable to the entire space station, which was launched by over 40 different missions and assembled in orbit. We need bigger rockets. In order to return, we need to use a propellant that we can synthesize easily on the Martian surface. Because of the presence of water and carbon dioxide, we can synthesize methane, a simple hydrocarbon that is perfectly good as a fuel. The challenge here, of course, is designing an engine that works efficiently with such a compound. Our current engines run on kerosene. Rocket engine CFD is hard. It's really hard. And I'll get to that a little bit more later. But for now, we can ask the question, why simulate it at all? We can build these things and test them on a test stand. In fact, that test you just witnessed occurs every single day at our facility in Texas. We test varieties of injectors. We play with parameters. We look at how tough the engines are, whether they can withstand the different demands that we put on them for the various missions we fly for our customers. So why simulate? The answer is because, as you can see from the video, it's very hard to get a glimpse inside the patient. There is no MRI into the engine. We can instrument the outside. We can look at the performance. But really, if we want to understand the combustion processes inside the engine, we have no easy way to do that. There's a tremendous benefit to being able to model the mixing in simulation directly. We can then optimize over a wide variety of injector configurations and test just a few. Another very important insight that can be gained into rocket engines would be that of combustion instability, which is the coupling of pressure waves and chemical energy release. That is a phenomenon that has delayed for many years many different engine development programs. It is the bane of engine development. You start it going, it starts to shake, and it either comes apart or it just continues to shake so violently you can't put any payload on top of the vehicle because it'll just shake it too much. So having insight into that from a simulation standpoint would be tremendously valuable. So what are the challenges? One major challenge that makes combustion CFD in a rocket engine different from other types of CFD, including aerodynamics and general fluid flow, is the wide variety of timescale here. So you can see we have, on the molecular scale, diffusion and reaction processes. We have flow fields at an intermediate timescale. And we have things such as acoustics, which again feed into combustion instabilities. We definitely would want to capture those. In addition, the combustion residence time is a very important factor. So one could say, and this is true, that the automotive industry has adopted combustion CFD, and it has yielded quite a bit of progress for that industry. In addition, the gas turbine industry also uses combustion CFD. In an automotive combustion chamber, you're doing a compression stroke, and at the bottom of that stroke, you've mixed your gases, and you ignite them, and the combustion process happens over a relatively short time scale. But by the time that piston reaches the top of its stroke, you're generally done with that combustion process, and you can then exhaust the products. In a rocket chamber, your propellants last for fractions of a second inside of this device before they're ejected out through the throat and expand out of the nozzle. That is a very important time scale to keep in mind. The chemical reactions, of course, happen on the nanosecond time scale. And we definitely want to get those right, because if you assume the reactions have reacted to completion, you're missing something, because in reality, the chemicals are reacting as they're injected, and then they're gone. And a lot of times, that reaction process hasn't fully taken place. Another major challenge of combustion CFD is the wide variety of length scales in the problem. So what I'm showing here is the energy cascade diagram. And the easiest way to understand this is to consider a cup of coffee. When you stir your cup of coffee, after some amount of time, it actually stops rotating and comes to rest. And what that is you're putting energy into the coffee. You're mechanically stirring it in a big circle, and you have this large structure. But due to the viscosity of the fluid, you get these little secondary eddies as the cream mixes. And you see those eddies get smaller and smaller until you get down to the level where viscous effects dominate. So basically, the friction of the fluid against itself dissipates that energy. And your cup of coffee is a tiny bit warmer because that's where your energy went. So the cascade of energy from where you put it in at large scales, in the case of a rocket engine, the injector, down to where it's dissipated, in this case, the Kolmogorov scale, or the scale at which these structures dissipate into thermal energy, which incidentally is the scale at which combustion mixing happens, is about 6 orders of magnitude, a factor of 1,000,000. So if you think of subdividing any sort of CFD mesh by powers of 2 over and over again, you need to subdivide it about 20 times in order to span that dynamic range of length scales. If you were to uniformly populate a grid on the order of a combustion chamber and injector, it's about 1 meter cubed, we're talking about yottabytes of data. Just not feasible, not really a reasonable thing to look at. So there must be something we can do. And in fact, typically people will do closure models for the turbulence. They'll resolve down to some scale and say, OK, we don't know what's happening below that. And that's just because you can only have one or the other. You can either have a big simulation domain, and you can look at a lot of different things, or you can really zoom in and get the detail right. Why not have it both ways? So let's look at turbulence itself. The interesting thing about turbulence is that although there is structure present at all scales, it's not dense. You don't have to resolve down to the finest scales everywhere. It's really fractal in nature. The interesting structure that you see actually doesn't fill the entire volume. This lower or fractal dimensionality allows us to concentrate computing resources where it's needed. You can think of this as just a glorified compression problem. When I compress an image, I want to be able to put it on disk and carry it around, and then decompress it to look at it when I want. When you compress turbulence, what you want to do is you want to calculate on it. You want to actually evolve these fields in time. So the real challenge is that you want to do all of the mathematics without decompressing the image. Because if you decompress it, now it takes up all this space that you don't have on something like a GPU.
Thanks, Adam. So now I'm going to dive a little bit more into the technical detail, the implementation of how we approach some of this compression, right? So as Adam said, we've got potentially this vast amount of data. And the traditional ways you break your data up for simulation are through a regular structured grid. It's very easy to manage. It's yottabytes of data, as Adam pointed out. And so while you can capture every one of those tiny little turbulent eddies at the finest detail, you literally can't store it. There's no machine in the world that has that kind of memory that can process that kind of data. On the other extreme, a far better way to map your problem space to the data is to create an unstructured grid with detail where you need it and less detail where you don't need it. And that's very good for static types of problems. But for something like turbulence, where you're generating eddies, they're changing in scale, shock waves are moving around, all of that kind of stuff, it becomes very, very expensive to readapt an unstructured mesh over and over again. So traditionally in these types of problem, and certainly the approach we're taking, is to go with an adaptive grid. The adaptive grid has sort of the benefits of both sides, right? It gives you the detail where you want it, assuming you can adapt cleanly, and I'm going to get to that in a moment. But it gives you the compression as well, the compression that you need so that you don't have to deal with these yottabytes of data. So let's talk about compression just for a moment. Something people are pretty familiar with, I think, is take on the left-hand side here, you've got a waveform of a musical chord. Right? It's a combination of notes, and as you know, these things are effectively a superposition of sine waves. You've got sine waves at the different frequencies, add them together, you've got a C major chord or whatever this happens to be. And typically, something we're all familiar with is MP3 music files, and there you will take the Fourier transform. You eliminate certain frequencies across the whole spectrum, so you keep some of the data that you need. And by strategically eliminating frequencies without really degrading the signal, you've compressed your signal and saved some space. And so one of the nice things about this type of spectral compression is that you can dial in and out the quality of the compression, the degree, by deciding how many frequencies you're going to eliminate. Now, the difference between something like a musical tone, which repeats itself continuously, which is periodic, and a physical simulation where you've got lots of localized data, is that this type of sinusoidal infinite signal really doesn't map as well to the kind of data that we need. You end up with a very thin, small delta function style spike costing you heavily because you've got to have high frequency data across the whole domain. So instead, what we've looked at is something called wavelet compression. Now, some of you will be familiar with this from say, JPEG, and I think H.264 uses it. I'm not quite sure. But wavelet compression is a similar kind of multi-resolution thing where you've got different frequency scales, different scales superimposed on top of each other. But the wavelet function is localized. Instead of using a sinusoid, which spans across your whole domain, you're using a local polynomial function, like a quadratic or even just something linear, or a quartic, or whatever you want to use. So what this lets you do is it lets you map a function at each location of exactly the size and resolution that you need. So you could have a domain in wavelet space which is built up of lots and lots of different small components and still achieve very good compression because your compression is so localized. That's exactly what we need with turbulence. With turbulence, we've got localized small eddies. You've got areas of smooth or large eddies where we don't need quite so much detail. This type of system lets us zoom in very effectively. The downside is, of course, computational cost. It's very complicated to do this at every single point. But this is where GPUs come in. GPUs give us an enormous amount of compute power. We can start to afford to do it. So what I'm going to do is I'm going to walk you through, just to give you a feel for how wavelet compression works, so that you can see how this multi-resolution picture gets built up. So imagine I've got a waveform. We'll talk about it in 1D. Obviously, this extends to 2 and 3 dimensions because we want three-dimensional simulations. But this here is, we'll take a one-dimensional signal, and what we do, we begin by sampling it. I've sampled it at all of those green points. I think I've got 24 green points there, and at nice regular sampling intervals. OK, so now we want to evaluate where we need to keep those points and where we don't need to. So what do? We knock out every other point. So I keep the even points, I knock out the odd points. So I've drawn as blue dots, or hollow blue dots, all of the points which I'm considering throwing away. Now, I want to be strategic about how I throw them away. So I'm going to draw lines between each of my green dots. The lines is my interpolation. If all I had were the green dots, that's what I would be able to draw. Now, my line comes closer or further away from some of my blue dots, right? So on the left-hand side, my blue dot is further away from the line. I can pick some arbitrary distance. I say if I'm further away than a certain amount, then my line does not correctly approximate this point. So on the left-hand side, I've got a point too far away. It's the delta, the distance between the point and the line is above some tolerance that I specified. And so what I've done is I've filled that in. I filled that blue dot in to say I'm going to keep that blue dot. Now, to the right, the next point, that's much closer to the line. That's inside of my tolerance. So I'm saying, yeah, OK, my line's a good enough approximation there. So I'm going to leave that one gone. I'm going to just use the line instead as the close enough approximation. So what I've done is I've filled in all the blue dots I'm going to keep, the ones too far from their lines, and I've left hollow all the ones that I'm not going to keep. And so what I can do is in my output array, my storage, I'm going to keep all of the filled in dots because they're the ones where my linear approximation was not good enough. Remember, this can be quadratic and polynomial in different ways as well. So I only keep the ones that are significant. So excellent, I've done one step. So get rid of the blue dots. Look at now only those dots, which are only the green dots, and we repeat the process. So remember, this is a multi-resolution compression. I've started out at the high resolution, and now I knock out my even points again. Sorry, I knock out my odd points. I keep my even points. Now I've got 4 green dots, some other number, 5 green dots. I draw lines between them. And I pick my blue dots and say, OK, which ones of those are going to be close enough, which ones of those are not going to be close enough, and I save them. And I can repeat this process time and again, saving some points, knock out my middle ones, draw lines in between, and record the data that's too far away. And you'll see, as you notice, each time I'm getting a coarser and coarser approximation here. And so this is the multi-resolution nature of the wavelet transform. And what this does is if I've got a very small detail, like a very fine turbulent eddy, I'll have captured it at the high resolution. If I've got something smooth or large, it will only start to be important at this lower resolution. And so the data that I save depends on the detail in my data, in my simulation data. So finally, my last point goes. And then all I have left are a couple of my anchor points. I've left those in green. You need to start somewhere. So we always record just a handful of points across our mesh. So we can say these are the points with real values, because everything else can be built back up from them. So if we look at the final data that we've got, I filled in all the dots that we actually kept. You can see out down the bottom that the ones which are hollow is data which I'm not even keeping. I've kept around about, I don't know, 18 or 16 or something out of 20. It's about a 40% compression ratio I've got. And you can see that the green dots are clustered around the areas of greatest change. So on the right-hand side, where my curve is more squiggly, then my green dots are more plentiful because they need to be tighter tracking of that function. On the left-hand side, I've got lots of smooth sections. I didn't need so much data. So my data, over the course of this transform, has isolated itself to those places that I needed the most attention, that I needed the most resolution. And this is the key to the compression. And by using that one tolerance factor that I showed you earlier, we can control how good our fit is all the way through, so that the data that we have through that tolerance factor can be matched to the accuracy of our physics that comes out at the end of this. Because we're going to take derivatives. As Adam said, we can't afford to decompress this all the time. We're going to take derivatives on this compressed data. So I'll go through decompression with you briefly as well, so you can get a feel for putting it back together. It's like all good compression schemes, it's easier to put back together than it is to take apart. But this is pretty symmetric. With decompression, I would just start with my green dots. Remember, they're my anchor points. I draw a line between them, and I look at the midpoint. Now, the midpoint in this case was a filled-in blue dot, so I've got a real value there. Remember, it was the distance between the dot and the line. So I can just add that distance back in, and now I'm back to two lines. Because in the same way that I got coarser as I created my transform, as I decompress, I'm going to get finer and finer and finer. It's literally the inverse of what I was doing. So now I take the next two midpoints. You'll see the one on the left is filled in. The one on the right is actually hollow. We decided, oh, this one here is close enough to the line that we're going to say the line is good enough. So when I put that one back together, when I put this set back together, I'm going to bump up the left-hand side, but the right-hand side, that hollow dot just stays on the line because I have no other data for it. That is where my loss arrives in this lossy compression. And I can keep on doing this. Midpoints of all those lines, midpoints of all those lines. And what I end up with is a wave that looks kind of like my original thing. It's not quite. You can see where I've lost detail. On the left-hand side, there's that dip. And that dip is not well approximated because my tolerance was too coarse. If we wanted to catch something like that, if I'd tightened up my epsilon, tightened up my tolerance a bit, we'd have got an extra point in there, we'd have mapped it. But you set the tolerance to what you want, and you get a reasonable approximation. On the right-hand side, that peak would never have been captured because it fell between 2 points at the finest sample resolution. The only way to capture that peak would have been to double my resolution, which is potentially quite costly. So you do lose the highest frequencies, which is normal in a spectral type of method. So if you look at the grid at the bottom, it literally is a grid at the bottom. Every point that's filled in is a point that is significant, and every point that is not filled in is just a gap. And I can actually represent that. I can draw that. If we look at 2 dimensions, I can draw it as a mesh. And what I've done here, what we've got is we've got an empty mesh, nothing going on yet. We've dropped an object in the middle of the mesh. Now, that object is just a simple 2D simulation so that we can show you. Remember, all the stuff that we're going to show you is output from our code. This is real physics that has been calculated using exactly these techniques. And we've dropped a profile of our Dragon capsule into the middle of this mesh. And you can see where the grid has automatically refined itself around the outside of that object. So far away, it's very regular, it's very coarse. and close into the object where you're going to get boundary layers, where you've got a lot of rate of change, the mesh is so tight that you can't even see the cells. It just looks like a blur of white. And you're going to see that repeatedly, where the mesh has so many levels of detail that in the finest areas, all you're going to see are white lines. So if I play this, and this is a supersonic flow developing around our capsule as it re-enters the atmosphere. This is traveling about Mach 1.1 at this point. You can see the shock wave developing around the front end of this. You can see the trailing wake shocks coming off as well, and the wake coming off the capsule. This is purely visualizing it in the grid space. That is how the mesh adapts time step after time step. And we apply this transform over and over again. Every time we modify the flow, we reapply it, figure out where does my resolution need to be now. I've got my grid at time t, my grid at time t plus 1. What did I have? What can I coarsen? What do I have to refine? And so at each of these grid points, we do calculation. So this is a picture of the specific internal energy, if you like, the temperature of every point on this grid. And you can see here, well, this is a really beautiful example, actually, of how when one of these capsules re-enters the atmosphere, the heating on the capsule, the reason you have a heat shield and it gets so hot is not because of friction. It's not because you've got friction of the air rubbing past the capsule. It's because the compressive heating of that enormously powerful shock wave in front of it leads to very hot gas behind it. And you can see the front curve of the shock with unheated gas, and you hit the shock, and boom, suddenly it's bright red, yellow. It's extremely hot right in front of the capsule there. And that's why we need the heat shield on the capsule. What I love about this is actually the trailing edge. You can actually see where those two shocks coming from the back have combined, and they've reheated that gas, and you're getting an extra hot bit of gas in the wake there. It's absolutely beautiful. So let's see this in action another time. This is, here I've got, and this is kind of like the most basic of CFD simulations. This is subsonic flow. I've got an object, and I'm just looking at the vortices being shed off my object. If your CFD can't do this, then you should just go home, because there's nothing else. You're never going to make it. So, sorry, that's a bit derogatory. Anyway, so you can see the vortex structure coming off the back of this. This is subsonic, no shock wave, same object, but later in time, if you like. And you can see the detailed structure following it in its wake. So if we play that again, and this time we superimpose the grid lines over the top, you'll see how the grid lines map and follow exactly where that flow is. So you can see those vortices underneath it. You can see the curls of the grid as they map to that flow. And so we're tracking temperature and density and every single flow property that we've got. The grid is adapting to, so that we lose none of that detail, or at least no more of that detail than we've specified in our lossy in our compression tolerance. So great. We've got a mechanism to get a grid, and it automatically adapts to not just our objects in the system, but to the flow around it. I don't have to map an entire giant high-density wake to capture that vorticity. It just automatically conforms itself to that vorticity. That's incredibly helpful. It saves me an enormous amount of compute power. But it does present another problem. It presents the problem of data indexing. So this is something which will be familiar to anyone who's done unstructured or dynamic grid codes of any kind. That for a regular grid, it's very easy to say, OK, I've got a point at x, y, z. My point at x, y plus 1, z is trivial to find. But if I've got a sparse grid of some kind, then there's no obvious relationship between the two. And so I've got to create some kind of data structure by which I can locate any 2 points, even 2 points which are conceptually next to each other in space, and not necessarily anywhere near each other in memory. So there are a few ways people do this. One traditional way is to map all of your data to a space-filling curve, so your neighbors tend to be close to you, and just do a linear search back and forth from where you are. That has obvious drawbacks, but it can be very efficient for good close neighbors. On the opposite extreme is a tree-based search, where you've got a known number of steps you have to take as you walk a tree, like an oak tree, for example, to locate your point. So even your neighbor has a fixed cost, but it's a fixed cost. It's much more predictable than something like a linear search. Typically, you end up with combinations of these things, some type of hybrid. The best one, which I'm aware of right now, is what's called a VDB tree. That's a very wide fan-out tree, so it has very few steps before it hits a dense leaf node. And within that dense leaf node, I can very rapidly look up my data. It's heavily used in the visual effects industry and in Hollywood. It doesn't have so much application yet in science, but I reckon that's really a really interesting thing to be looking at. So how do we do our grid? Well, one of the problems with a large grid of data is moving all this data around. So the first thing we're going to do is we're going to abstract our grid away to just a simple location code and an indirect reference. And yet, I know that's pointer chasing on a GPU. That's something which is normally frowned upon, but I'll get to that as well. But starting out, every single grid point, I'm keeping just two pieces of information that I need to care about: where it is, X, Y, Z, and where it's pointing to in my huge, giant, not quite yottabytes array of memory. So my grid is effectively just a giant array of these, a giant array of locations and references. It means that something at position 14 in my grid and something at position 15 in my grid might not point to anything like the data that's next to them. So maybe the point in 11.11.5 points to grid item, to item 3, and 11.12.5 points to item 8. So I just can follow my reference. And that tells me exactly where to find my data. So already I can do all of my complex and repeated elaborate grid manipulation without having to mess around with my data any more than I need to. So far so good. I've got a nice convenient grid. Let me show you a bit how that applies to something like adapting a grid to a wavelets. Remember, I've got my wavelet function, bunch of dots. I'm going to subsample that by half, right? So all of my dots right now are lined up 0 through 9. I've picked out half of my dots. I've done whatever I need to do. And then I blow away my blue points. I blow away my blue points, and now my green dots, instead of being at point 0, 1, 2, 3, 4, 5, they're now at 0, 2, 4, 6, and 8. You can imagine if I do this repeatedly, after 10 levels, I'll have a stride of 1,000 between them. After 15 subdivisions, I'll have 32,000. That's a stride that the GPU memory simply would not be able to cope with. You cannot go random accessing your GPU memory and hope to suck in the kind of data that we're talking about. But with this grid indexing, nice and easy. What do? As I blow away my interim points from my wavelet function, I also blow away my grid nodes. Now I just have 4 points. I pack them together, and now suddenly all of my points are accessing their neighbors again. So by being able to play around with this small and inexpensive grid reference structure, I more than buy back the cost of my indirect reference. Still not quite right there, though, and I'm sure you've picked up on that, and I'll tell you exactly why. So as I apply a bunch of transformations to my grid, I've got, here's a nice laid out, friendly set of things, 0 through 9, reference 0 through 9, everything's aligned at the beginning of time. As I go through adding nodes, deleting nodes, transposing them, resorting them, doing all the different types of things you need to do to a grid as you're manipulating it, I end up with things all shuffled around, right? So my grid index 0 through 9 is now pointing to 4, 7, 9, 0, 5, all over the place. Notice the location still maps up to the reference, right? I've moved the pairs around. They always move as a pair. So location 4 is pointing to reference 4 still, and location 1 is pointing to reference 1 still. They're just out of order in terms of my actual data. Why does this matter? Well, when I start out and I'm looking for my neighbors, I do need to know where my neighbor XYZ point is, x plus 1 and x minus 1. But I also need my flow data. I need my momentum. I need my energy. I need my density. I need all of those types of properties. And so as I shuffle my grid around, I end up shuffling my references. And so now my data no longer, for the data for 2 points, no longer sits next to each other. And that is going to be very painful. So what can we do? Well, a really convenient thing we can do is, it turns out that reference table is exactly what we need to unwind all of this. So after I've done all of these grid manipulations, because remember, we go through this whole wavelet adapting, compressing, everything process on every single time step. Once I've got it, my grid stays nice and fixed for all of the differential operations I need to make. So at the end, I do one reordering step based on what that reference number is. Notice that point 0 had reference 4, so I just pick out data at column 4, and I drop it into column 0. So my reference list tells me exactly the order which I need. And now my data is back one-to-one in a single pass of read-write through my data. It's a lot cheaper than moving my data around everywhere I go, and it saves me enormously in the long run when I need to be indexing my data and accessing data as high bandwidth as I can get it. The other nice thing about this is that when I find a point in my grid, say point 4 at x5, y5, when I find that particular location and it says, oh, you're at grid index 5, that's automatically at simulation data index 5. It's in my column 5. So I actually do not need to follow my reference anymore. I can skip that indirect lookup. I can skip that pointer chase, which is so costly on a GPU. Having found my data, I know exactly where to look for it in my main data array. So this saves an enormous amount of time. And that one permute at the end of everything means that I no longer have to pointer chase. So let's put it all together. So what we've got here, and I'll just pause it while I set up for you what you're about to see, because quite a lot goes on in this. What we have here is a box. And again, this is, as I say, all the simulations you see are simulations run through our code. This is a box of gas. It's pre-mixed gas of some fuel, some oxygen. And what we're doing in the bottom left-hand corner is we're going to ignite just a spot artificially. We're going to set it off. And then the flame front is going to start burning outwards. And it's going to first burn outwards in a bubble. But these are walls. The top, the bottom, and the left-hand side are all walls. So the pressure waves and the expanding bubble is going to bounce off the wall and come back in. And you're going to see it crashing into this expanding bubble of flame and distorting it with really interesting turbulence effects. We're looking at density here. So as things burn, it gets hot. The dark blue will be low density where it's hot. And you'll see all of the acoustic waves start traveling around. So as it expands, first the bottom and the left-hand sides reflect. And you've still got pretty steady burning, although you can already see in the bottom left-hand corner things are changing. You can see lots of these waves traveling outwards from it. Some come in reflecting off the top, slam into the bubble, and start distorting it and compressing it. Leading up ahead of it, you've got all these other acoustic waves adding onto each other. And so we turn on the grid. And remember I said to you, when the grid is really refined, all you see is a white blur because the cells are so incredibly fine. And you can see the grid tracking each of the wavefronts of these acoustic waves. If you look on the left-hand side, that blue area is actually where it's burning. It's where the flame is. And you can see that it's tracking so much detail in the flame. I'll show you on the next video exactly what kind of detail it's tracking. It's just really filled with detail on the left-hand side. But on the right-hand side, we're only keeping information exactly where those acoustic wavefronts, those pressure wavefronts are. If you actually did this as a fully dense calculation, this would be 300 million grid nodes. We did this on a single GPU because we're only calculating it where it needs to be, and it figures out for itself exactly where that data needs to be. And so the effect, let's watch it from the flame side of things now. We ignited, and we're watching temperature at this point. And so you can see the flame beginning to form, and it gets hotter and hotter in the core. And it's burning in that bubble that you saw expanding at first. And again, what you'll see is, again, as the pressure wave travels down and hits it, it starts distorting that flame. It pushes it down in the top. And the bottom left-hand corner, there's a bit of unburned gas, something just reflected out of the corner there. And you can see it rolling up around that area. You can see those really, really fine vortices, this beautiful level of detail. There are 60, you could zoom in 60,000 times in this simulation and still catch data. That is how much detail there is on this. And you can see the beautiful, beautiful flame structure forming in the top corner. And all of this is because the grid is tracking every single little loop, every vortex, every little flame front. And so that is a snapshot in microsecond time of how this exploding flame is forming. I'll leave it to Adam to tell you about the rest of it. That's the real world. Physics is art, man. Physics is art.
So one of the real great takeaways of this is that you're very carefully calculating the mixing. So you had a little pocket of cold gas in that corner, and it had nowhere to go. So as the flame expanded, it pushed that cold gas in the corner where it became pressurized and came right back in the middle, and you saw it rise up and mix in all of these tiny little eddies. This was a pre-mixed combustion simulation. But naturally, these structures are significantly important in a non-pre-mixed combustion simulation, such as one done to evaluate a rocket combustion chamber. So another thing is to really highlight, work like this has been done before. People have been looking at wavelet compression schemes. People have applied them even to mathematical simulations. And in fact, A researcher named Jonathan Riegel has done a similar calculation of this. In fact, we've based this particular video on his work. The difference is without GPU acceleration, without the architecture combined with the techniques that Stephen just described, it takes months on thousands of cores to run even the simplest of simulations. It's a very interesting approach, but it doesn't have industrial application without the hardware and the correct algorithms behind it. So what the GPUs are doing here is enabling tremendous acceleration. And I'm grateful to SpaceX for letting us start basically from scratch on CFD and in many ways reinvent the wheel. And people say, why would you do that? Well, the reason you need to do it is if you're a little bit wrong in a traditional CFD simulation, you're typically OK. You're close enough to the answer that you can make an engineering decision. In a combustion simulation, if you get it wrong, you have to deal with the vicious interplay and nonlinearity of all these different physical processes. For example, if you're near a vaporization point and you get that wrong, all of a sudden your density is swinging wildly. If you don't have temperature-dependent viscosity, you're going to see the wrong effects in a nozzle. And we actually are going to show that in a moment. If you don't get the temperature right, well, that's where you're really in trouble, because your chemical reaction rate is exponential with the temperature. So if you're a little bit high on the temperature, you have an energy release that's a little too high. And instead of restoring you back to where you should be, it actually drives the temperature higher. So combustion CFD is very demanding, and that is why techniques like this aren't just cool, they're absolutely essential to tackling these problems. In addition, GPUs are great for the compute-rich aspect of the chemistry. So typically we think of something simple like hydrogen and oxygen reacting into water. But the reality is that there are intermediate products, and there are forward and backward reactions. And to even put in the simplest model here, we're talking 23 reactions, 11 species. And this is a reduced mechanism. So you can run this in a massively parallel fashion because it's just the local properties at each point that determine the chemical reaction rates. Thankfully, we're doing methane. We're not doing anything, no big hydrocarbons, at least not yet. And so that is tractable on a computer. But it is a challenge. There are over 325 reactions to consider with 53 intermediate species. This is not to be taken lightly. And having the ability to have a massively parallel system crunching this is invaluable. I actually have to pause to let it finish scrolling. So it really gives you a taste of, if you can reduce the requirements, if you can reduce the number of grid points you have to keep active, you can use that otherwise wasted resolution on something more valuable, like a chemical reaction calculation. Let's put it all together and see what that looks like. So what we're looking at here is Mach number. And again, it's coming straight out of our code. This was run over the weekend on a single GPU. And you can see the development of the sonic throat, and you can see the supersonic flow just downstream of the throat. And you can see some interesting features. This is called a Mach disk and trailing Mach diamonds. And this is all produced naturally from the code. The grid is automatically generated, and the basic laws of physics combine to give us these great structures. And you can see here is a picture of the Space Shuttle main engine with that Mach disk, which is a place where you have supersonic flow suddenly decelerating supersonic to subsonic. So it starts off supersonic in that nozzle and immediately across that shock becomes subsonic, and the density increases, which is why you see it white. So there are other applications of this, not just combustion CFD. We've chosen combustion CFD because this is really an enabling technology that allows us to tackle problems that have never been tackled before in combustion research. Aerodynamics is another area where CFD is used widely. And the CFD in aerodynamics is very effective, but it's expensive. One of the things that we always talk about is in visual effects, you fake the physics any way you can, and you make it look pretty, and everybody gets excited and they love it. In research, you try to get the physics just right, but it ends up looking kind of blah. Your visuals aren't as stunning. And people go, well, wait, I saw a movie the other day with a simulation. Like, why can't you just do that? So a friend of ours actually ray traced actual simulation output. So what you're looking at is the bow shock around a re-entering Dragon capsule. This is the actual data from the simulation with the CAD model and some ray tracing put in. And the beauty of this is that we can use it for other applications. We can speed up these processes, which can typically take half a year or more to do a full, detailed suite of calculations to evaluate the aerodynamics of a vehicle, and just dramatically bring that time in, which again, going back to the original theme, makes it so that the engineers can focus on fewer tests and more rapid development. And here's a nice video of this in action. The nice thing about this is that we're able to connect better with people and engineers by having visualizations like this. And at the same time, we're still maintaining full fidelity of the data. So I had mentioned that this work is based on the research of many other people. I'd like to acknowledge some of them. This is by no means a complete list, but there have been some very brilliant people working in this space. What SpaceX is bringing to the table is an application of these very powerful mathematical techniques to the GPU. I highly recommend you look up the research of these folks. It's very, very good. And finally, I just want to thank everyone again for being here, NVIDIA for inviting us, and SpaceX for making this all possible. Thank you.